Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lecture. Today we will look into 3D point groups and then we will see the origin of piezoelectricity. So, in 3 dimensions the symmetry element also can be combined in various way, but the combination has to be consistent, which means the combination should give something which is meaningful and realistic. So, with that there are total 32 combinations possible and we will look into these combinations. Now, here we will not draw the combinations, but rather we will look into them with their symbols. So, there is Harman Mogwin systems or Mogwin symbols to define these symmetry elements in 3D point groups. So, this is internationally accepted notation. There are other systems also like Schonflies, but we will here look into only Harman Mogwin symbol. So, in this system a rotation is denoted by numbers like 1, 2, 3, 4, 6. Roto inversion is denoted by 1 bar, 2 bar and so on. A mirror, which means a reflection plane, is M, and also elements which are parallel are written one after another. Like 2M, a two-fold axis and a mirror parallel to the axis, and elements perpendicular are written with a slash. For example, a two-fold axis, if there is a mirror which is perpendicular to the axis, then it is 2/m. Now, let us look into this. So, at first we have 1, it is just 1, means one fold axis, and one fold axis does not mean much. So, it is 1, and then comes 1 bar, it is one fold roto inversion axis, and this is in the triclinics, this is the category of triclinic. So, these are triclinics, and then comes these 2, 2, 2, 2, and these are monoclinics. And then we have three, they are orthorhombic, and here we have tetragonal. Now, this just means that it has one fold axis of rotation, and this means 1-fold axis of rotation plus inversion. So, it is a roto inversion, 1-fold axis of roto inversion. This simply means 2-fold axis of rotation, and here there are 3 2-fold axis of rotation. So, 3 2-fold axis. Now comes something where we have a mirror and which is perpendicular to it. So, it is 2-fold axis and a mirror perpendicular to it, perpendicular to the axis of rotation. 6 means, I mean at number 6 we have just M. So, M means just it has one mirror. So, it has one mirror plane. Then we have 2 mm. 2 mm means 2-fold rotation axis. So, number 7 is 2-fold axis and 2 mirrors, they are parallel to the rotation axis. Then number 8 has triple M, it has 3 mirrors. Among those 3 mirrors, 2 are parallel and 1 is perpendicular. Number 9 is just 4-fold axis. At number 10 we have 4-fold axis of roto inversion, which means inversion plus rotation. Then if we move forward, we have these are all tetragonal, and then these are all trigonal. So, at 11 we have 4-fold axis and 2-fold axis. So, it has 4-fold axis, here axis means axis of rotation, and 2-fold axis. Then we have 4-fold axis and 2 mirror planes. Which are parallel. Then we have 4 bar 2, which means 4-fold roto inversion, and 1 2-fold axis, and then 1 mirror. And this mirror is diagonal to it. Then we have 4-fold axis and 1 mirror perpendicular to it. Mirror perpendicular to it. Then we have 4-fold axis and then 3 mirrors . 3 mirrors, and these are perpendicular to the rotation axis, and we have 3-fold axis for 16, and for 17 we have 3-fold axis and 2-fold axis. For 18 we have 3-fold rotation axis and a parallel mirror plane. And mirror which is parallel. Then we have 3-fold roto inversion, and then we have three-fold roto inversion and one mirror. This mirror is diagonally placed, and then we have 6-fold axis. Now, if we look at the last 6, then these are all hexagonal, and these are all cubic. So, number 22, it has 6-fold roto inversion, and then number 23 we have 6-fold axis and 2-fold and 2-fold axis. And 2-fold axis. And then we have 6-fold axis. Here we have 6-fold axis and 2 mirrors and 2 mirrors, and they are parallel. And then we have 6-fold roto inversion, then mirror, and then we have 2-fold axis. Here we have 6-fold axis and one perpendicular mirror, which is perpendicular. And then we have 6-fold axis, and then we have 3 mirrors. These 3 mirrors are all these mirrors are perpendicular to the 6-fold axis, and so perpendicular to the axis. And then we have 4 bar 3m, so it is a 4-fold roto inversion, then a 3-fold axis and a mirror. And a mirror. In 29 we have 4-3-2, 4-fold axis, 3-fold axis and 2-fold axis. Then we have 2-3, 2-fold axis, 3-fold axis, and then 31 we have mirror, but this is perpendicular to 3-fold roto inversion. 3-fold root inversion, and here we have mirror 3-fold axis, and then we have mirror, and again they are perpendicular to each other. So, total we have 32 elements here, and so we can see that out of these 32 point groups, there are few point groups which are centrosymmetric, which are center of symmetry, and they are marked as red here. So, we can see few here, we can see few here, we can see few here. So, they are total 11 in numbers. So, out of those 32, 11 are centrosymmetric. So, those which are centrosymmetric, they do not show any piezoelectricity. Now, the question is, what does centrosymmetry has to do with piezoelectricity? That we will talk about after few minutes. So, out of these 32 point groups, we have centrosymmetric, which are 11 in numbers, and then there are rest 21 which has no center of symmetry, and then out of those 21, just one is non piezoelectric, and there are rest 20 are piezoelectric, and then out of those 20, 10 are polar, or we can call pyroelectric. Now, what it means, we will see it after some time, and 10 are non-polar. And again, out of those 10 polars, we have some as ferroelectric. So, in ferroelectric, the polarization is reversible, and some has non-reversible polarization. Now, the question is, what does this absence of centrosymmetry have to do with piezoelectricity? That we can understand by these two examples here. Here we have NaCl, it is centrosymmetric. So, the center of the positive charge and negative charge are coinciding. Now, if we apply stress to it, suppose if I compress and suppose it deforms into this shape, then also because of its centrosymmetric nature, the center of the positive and negative charge remains coincident. So, then they do not separate, they do not form any dipole. So, the center of the negative is here and center of the positive is here, and they are at the same point. Now, let us look into this ZNS. So, this is piezoelectric and this is not centrosymmetric. Here at the beginning, the center of positive and negative charge are same. Now, if we apply stress to it, it deforms in this fashion, and in this situation the center of the negative charge is here and the center of the positive charge is here. So, here the centers of positive and negative charge separate, and then they create a dipole here, and that is how the piezoelectricity originates. So, if it is not centrosymmetric, after deformation the center of positive and negative charges separate and dipole is created. Now, let us look into the different types of dielectrics. We have seen various other terms like paraelectric and ferroelectric, pyroelectric and so on. So, now let us define them. In paraelectric materials, they are centrosymmetric and they are non-polar. So, electric field, it leads to dipole and then deformation comes. So, electric field leads to dipole and because of those dipoles the material deforms. Now, here the relation between the deformation and electric field is proportional to square. So, if we plot the electric field and the deformation, it looks like this. It should look kind of symmetric with respect to the vertical axis. So, it looks like this. And we have seen that this is seen in materials which are electrostatic. So, it is a phenomena of electrostriction. So, we have seen that all the dielectrics show some kind of electrostriction, but in some of the materials it is quite less, in some of the materials it is quite high. Piezoelectrics, they do not have center of symmetry. Here due to stress, dipole moments can be generated, just we saw how it generates. In piezoelectric materials, if we look at the relation between electric field and the deformation, it is like this. So, when the field is changed, the deformation reverses. So, in this case, in case of electrostriction, the deformation is somewhat proportional to the square of the electric field. In this case, the relation is linear, but in very high electric field, the linearity does not hold. The relation starts becoming non-linear. Then comes pyroelectric. Now, in pyroelectric, they do not have center of symmetry, but they have spontaneous polarization. So, even if we do not apply any pressure here, they already have some polarization. So, these materials are pyroelectric material. Now, why is it called pyro? Pyro means has something to do with heat or temperature. So, here temperature causes expansion or contraction and which changes the dipole. And when the dipole is changed, surface charge generated. So, temperature indirectly leads to surface charge generation. So, that is why it is pyroelectric, and this expansion or contraction due to temperature has opposite effect of surface charge generation. Ferroelectrics, they have center of symmetry and they have spontaneous polarization, but here by applying electric field, the field orientation of the polarization can be changed, and there are some material where it cannot be changed. So, that is why some materials within pyroelectrics are ferroelectrics and some are not. Now, piezoelectric materials are available in various forms. We have seen that piezoelectricity is there in single crystals like quartz, berlinite and so on, and there are piezoceramics which are polycrystalline in nature. Examples are lead zirconate titanate, PZT. So, PZT is the most commonly used piezoceramic, barium titanate and so on, and there are polymers also polyvinylidene difluoride. So, PVDF and other polymers. Now, we have looked into their relative merits and demerits. They have strong piezoelectricity, and here it is more flexible, but they have less piezoelectricity. So, depending on the application, some are used and some are not, and also there is something called piezoelectric composite, which is made of more than one materials. So, to harness the benefit of one material over other, and also with piezoelectric composites directional actuation sensing is also possible. Now, we will understand what piezoceramics are. To understand piezoceramics, we have to see what perovskites are. So, perovskites is a structure which is shown here, and these are exhibited by materials like lead zirconate titanate, barium titanate. So, they are rhombohedral, tetragonal or orthorhombic, and they show spontaneous polarization below a temperature called Curie temperature. So, each of these perovskites below a temperature called Curie temperature show a spontaneous polarization, which can be understood here. In this structure, we can see that this barium and ions are positive. So, they are sent. So, their net charge is here, oxygen's negative. So, the net negative is here. However, this titanium ion is shifted little up or down, so that creates a dipole. So, below the Curie temperature, because of this kind of structure, it is polarized. However, above the Curie temperature, this titanium comes at the center. So, now there is no dipole. So, this is the same thing when we see it from one side, the above and below the Curie temperature. Now, as we saw at the beginning that the polycrystalline materials have different domains, and within different domains orientations can be different. So, we have seen that these perovskites have dipoles, and if we just go back. So, here the polarization direction is P this, because it is going from negative to positive. Positive is up here. So, negative to positive, that is the direction of polarization. Now, in polycrystalline materials, each of these domains have different domains of polarization, because the individual domains have their own orientation or distribution. But when we look at the full picture, the net effect is a zero polarization, because of these diverse orientations finally they balance each other, and we do not see any net polarization if we look at the full polycrystalline material. So, that is why something called poling is done. So, this material is put under a very high electric field, and that reorients these dipoles and brings it in this form. So, each dipole is now oriented depending on how we apply the electric field. So, if we apply the electric field plus here minus here, the dipoles are oriented in this direction, in this way. So, once they are polarized, now they can be used as piezoelectric crystals. However, the relation between the electric field that is applied to polarize and the amount of polarization that we get is not very straightforward. So, if we plot electric field in this direction and polarization in this direction, suppose we start from here, it increases like this, and after a certain electric field it saturates. So, beyond this, if we increase the electric field, we do not get any more polarization, and then if we bring it back here, we get something called a residual polarization. So, here it is, we can call polarization as the saturated form. Here we get polarization which is left after the field is made 0, we can call it PS, and then the graph looks same at the other side also. If we start from 0, here the graph would gradually come here and go back. So, in this hysteresis diagram, these are the arrows, it increase like this and it decrease like this. Now, when the electric field is very small, then P is assumed to be proportional to the electric field, and that we will do when we find out the constitutive relation of these piezoelectric materials. So, this is a piezoelectric material, that is, it is a view of the piezoelectric material that is available commercially. So, it is poled. So, for polling, electrode is applied at the top and bottom, and using this it is poled, and this polarization mark shows the direction of polarization. It is not necessary that it has to be polarized along the z axis. Electrodes can be put at the other surface also, and it could have been polarized in other directions also. But for most of the practical applications, the piezoelectric sheets that we get are polarized along the thickness direction. Piezoelectric ceramics are generally obtained in two different forms: PZT ceramics, hard and soft. Now, PZT ceramics are solid solutions of lead zirconate and lead titanate. They are often doped with other materials to obtain specific properties. Now, depending on the constituents, the properties can vary. Hard ceramics are better for high force actuation, and soft ceramics are better for sensing applications. Here are some characteristic comparison. Piezoelectric constants are larger for soft ceramic and smaller for hard ceramic. Permittivity is higher for soft ceramic, lower for hard ceramic. Dielectric constants are larger for soft ceramic and smaller for hard ceramic. Dielectric loss is higher for soft ceramic and lower for hard ceramic. Electromechanical coupling factor is larger for soft ceramic, smaller for hard ceramic. Electrical resistance is very high for soft ceramic and lower for hard ceramic. Mechanical quality factor, they are low for soft ceramic and high for hard ceramic. Coercive field is low for soft ceramic and higher for hard ceramic. Linearity is poor in soft ceramic, and in hard ceramic it is better, and polarization and depolarization is easier in soft ceramic and more difficult in hard ceramics. This comparison can be found out in the book. Now, suppose we have a piezoelectric sheet which is poled along the thickness direction, and then if we apply the voltage in such a way that the actuation electric field matches with the electric field that was used for polling. Now, here the direction of polarization is shown negative, which means to get this kind of polarization, the electric field that was used for polling should have been also like this, should have been plus up, minus down. Now, we are applying electric field in the same sense. So, we are applying the voltage like plus up and minus down. If we do that, then the material thickens along the material thickens. So, its dimension increases along the thickness direction, and accordingly it reduces along the other two directions. This can be understood from again from this perovskite structure. So, now because the polarization is like this, which means the structure is in this form, the titanium is here shifted down. Now, if electric field is applied in such a way that it is plus up and minus down, so this is further shifted down. When this is further shifted down, the thickness increases and accordingly the other two dimension decreases. Reverse thing happens if we reverse the applied electric field. So, that was about the inverse effect. Now, while doing the direct effect, again assume that the polarization is from positive to negative, which means the titanium is at the lower side. Now, if we apply tensile stress along the thickness direction, if we want to increase this dimension, in that case what happens is, if you want to increase it, the distance between this titanium and the center further increases. and that creates an electric field which is plus at this side and the minus at this side. And again the reverse thing happen when we apply compressive stress along the thickness direction. So, with the help of this perovskite structure, we can explain this phenomena, the direct and indirect phenomena, when it is, where it is stretching, where it is contracting, or when it is applying a plus a positive voltage, when it is generating a positive voltage, when it is generating a negative voltage, and so on. Thank you.